Now we're going to look at some limits that we've already seen to this point, but we're going to look at them a little more closely. We've come across infinite limits. That means like limits where the answer is infinity or negative infinity. And then we've also seen limits at infinity, meaning as x approaches infinity or negative infinity, we've done some of those limits as well. These two limits come up and relate to horizontal and vertical asymptotes in different ways. So we're going to talk about rational functions because it has those types of asymptotes, and these limits come up quite often. So here's an example of two different rational functions. And remember, a rational function is one polynomial divided by another. On this first page, we're just going to sort of go over the graph. So for us to have an infinite limit where the answer is infinity or negative infinity, typically in these functions, is going to be a limit. Oh, that's weird. As x approaches a, typically from one side or the other. So I'll say left, right or left, where a is a real number. So we're not talking about x approaching infinity or negative infinity. So that's the first thing, and it's going to be one-sided typically. The result, these are the two things we kind of want to know of what I've said in the opening, is always negative infinity or positive infinity, indicating the existence of a vertical asymptote at x equals a. So let's look at these here. So on this first graph here for f and g, the limit as x approaches 2 from the left, and we're on the graph f. So as we approach 2 from the left, we are approaching a vertical asymptote, and you can see that the height of the graph goes down to negative infinity. So that is our answer. As we approach 2 from the right, we're approaching that vertical asymptote from the other side. The function is shooting up to positive infinity, so the height is approaching positive infinity. And that's just kind of showing you what I talked about there in that first infinite limits box. Now we're going to look at the other function, -1 from the left. Again, we're approaching that vertical asymptote from the left, and the graph is shooting down to negative infinity. And then we look at -1 as we approach from the right. We're on the graph here shooting up to positive infinity. So those are our limits there. Those are called infinite limits because their answers are either infinity or negative infinity. Notice over here, for limits at infinity, we're talking about limits that approach either infinity or negative infinity. And what that really is has nothing to do with vertical asymptotes now. We're going to pay attention to horizontal asymptotes, slant asymptotes, because those are end behavior. Because when we talk about x going to infinity, we're talking about the right side or the right end of the graph. So some things that we want to summarize about limits at infinity. A limit where x is approaching infinity or x is approaching negative infinity. That's what we mean by limits at infinity. And the result, we're going to talk about what kind of answer you get in these situations, is always one of three things: negative infinity, positive infinity, or a value, a real number. This indicates, we use the end behavior to indicate what this is. So I'll say indicating the end behavior of the graph. So let's see what we're talking about here. So the limit as x approaches infinity on f. So as x goes all the way to infinity, we're talking about the right end behavior. And so when we look on the graph, we see that it's approaching that horizontal asymptote of 2. So if we didn't have the graph, because we're going to be able to do these without graphs, it's more important that you can go backwards, the whole indicating the end behavior of the graph. So once you find out the limit as x approaches infinity is 2, you're going to say that the right end behavior, it's approaching a horizontal asymptote of 2. So over here, as on f, as we go to negative infinity, on this side, it's also approaching that horizontal asymptote of 2. On the function g, as x approaches infinity, we're now approaching this slant asymptote, and it's not bounded. It's just going to keep going up and up and up. This graph, right, just keeps increasing with the asymptote. So that's going to actually be infinity. And then on the left-hand side, as we approach negative, and x approaches negative infinity is on the left-hand side behavior of the graph. It's also approaching that slant asymptote, but that's just going down forever without bound. So you can see the example of we could get a number for an answer, or we can get infinity or negative infinity. So we're going to look at now, what if we don't have the graph? We have to come up with a process by analyzing the function for which we can find this limit, these limits at infinity. So on this one, it's saying for each one, find each of the following limits at infinity, give an explanation of your reasoning for each. So we're going to keep in mind that as x approaches infinity, we're talking about end behavior here. So I'm going to say I know that this is the limit is equal to negative infinity. What is my reasoning? Well, I would say something like, since the degree is odd and the leading coefficient is negative, the end behavior tells us that the function falls to the right. I guess that's how I would say it. You could probably say it better than what I just did. Now, I know it's right-hand side because the limit is approaching positive infinity. Or I should say x is approaching positive infinity. That means right-hand side. So I'm looking for the right-handed behavior of this thing. And we remember this stuff from pre-calculus. It's got to be in standard form, though. It cannot be in factored form. So that's what we're going to look at number 2. Do you actually have to multiply everything out? No, because you just need that figure. You just need that leading coefficient there. You need to know what the first term is, what its degree is, and what the leading coefficient is. So it looks like when we square this, an x, and we square it, we get x squared, and then times another x times another x. So it looks like it's going to be even. So we can start off by saying, since the degree is even, I'm going to stop there for a second. We have to figure out what's the leading coefficient, positive or negative. So when I multiplied this stuff out, I got basic in this, when I do 4 minus x squared, I don't need all the other stuff. I just need that first term. And that first term would be from a negative x times a negative x, right? Then whatever that first term is, when I distribute it into here, what's going to make the x cubed when I multiply it by the positive x there? And then when I take that polynomial and multiply into this guy, the one that's going to make the leading term is going to be multiplied by x again. So I can kind of just track those guys and see what their coefficient comes out to be. The negative times the negative is a positive, so then it's all just going to be that leading coefficient is going to be 1. It's going to be x to the 4th with a positive 1. So that's all I need to really analyze. So I'll say, since the degree is even, and I'll say LC is bigger than 0. That's a fancier way, or a neater way of saying the leading coefficient is positive. The graph will rise to the left. And it's left-hand side behavior because x is approaching negative infinity, so on the left side of the graph. All right, now we're looking at one that's not a polynomial. What do we do about end behavior when it's not a polynomial? Well, I know that this one is going to be equal to negative 2. Did I actually write an answer in here? I didn't. So since it rises to the left, the answer is infinity. Okay, sorry, back to this. I know this one's negative 2. How do I know that? Well, in a rational function, I'm going to say since the degree of the numerator and denominator are the same, there is a horizontal asymptote. I need to finish that word before I go on to the next word. At y equals negative 2 over 1, you divide the leading coefficients, which is negative 2. We saw before, if a rational function has a horizontal asymptote, that's the end behavior on both sides. So that would be, I would say, the graph approaches negative 2 on the right side. And you should be writing all this down because you need to practice the explanations, right? This is important stuff. Okay, so this comes down to horizontal asymptotes. Yeah, there's 3 rules for horizontal asymptotes. Maybe I can remind you of them in class when I need to. Or we may do it later. Actually, I'll do it later in this. I forgot. So we're going to do it later in this video. Okay, so let's look at another thing here that we got to kind of recognize about these rational functions. Okay, so we're going to look at these 2 functions and just kind of see what they have in common, both in their equations and in their graphs. So the first thing algebraically what we look at is I always have trouble spelling that word. Oops. So I'm going to say algebraically the numerators are what? Looks like they're just both a constant. And the denominators are some power of x. So that's the thing to notice in the equations, right? And then what do we notice graphically? We notice graphically that they both have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Now that's the important one. Let's go with pink. For our analysis of rational functions in end behavior and limits at infinity, horizontal asymptote at y equals 0 when we see that the numerators are constants and the denominators some power of x. That's the key. Because then what happens at the end behavior? The end behavior is going to approach 0 on both sides. We're going to use that to our advantage. It approaches 0, right? So that is really the key. Okay, so on this part, we're going to look at a little bit of a different way to think about it, or it kind of confirms what we know about the horizontal asymptotes of rational functions. Rational functions may have a horizontal asymptote, and we know that that horizontal asymptote tells us the end behavior. So that's great, because when we're looking for limits at infinity or negative infinity, they're asking what's the end behavior. So essentially, when you see this problem, the limit as x approaches infinity or negative infinity of a rational function, right, a fraction with x on the numerator and in the denominator, you're looking for the horizontal asymptote. So we know this limit here to be 0 because there's a horizontal asymptote at 0. And that is because the power, the degree of the numerator is less than the degree of the denominator. So you have to remember those 3 rules. When the degrees match, like this guy, I know that there's a horizontal asymptote at 2 over 1 which is 2. So if there's a horizontal asymptote at 2, that means the end behavior is 2, whether I'm going to positive infinity or negative infinity. And on this last one, it's a little bit different because we don't know that there's not a horizontal asymptote. When the degree up top is actually larger than the degree on the bottom, there is not a horizontal asymptote. So that one's kind of in question. I don't know the answer right away. I know that it's going to be a slant asymptote because the degree is exactly 1 higher. And on a slant asymptote, right, the graph either goes up on the right forever or down on the left forever, or the other way could slant that way and be vice versa. So I do know the answer is going to be positive or negative infinity. So I guess I can put those two options in. We're looking for the right-hand behavior on this, so it's either going to be that or that. That's what I know based on my analysis of horizontal asymptotes and end behavior. However, there's a little trick we can do here to do another type of numerical analysis using limits. So what we're going to do here and kind of confirm what we know the answer to be already is one trick that you're going to do is take and divide every part of this thing, of this rational function, by the biggest power of x in the denominator. And then simplify. Now all I've done really is multiplied the function by 1, right? Because it's like I've multiplied by 1 over x squared over 1 over x squared. When I distribute that to the numerator, let me do it up here. It looks a little weird. Let me get rid of that 0 for a second. What I've really done is multiplied by 1 over x squared over 1 over x squared. When I distribute this to the numerator, I'm just doing that multiplication, same thing on the denominator. And so I'm really just multiplying by 1. So I'm allowed to do that. When I simplify, a lot of nice things happen here. So I'm going to get 1 over x plus 2 over x squared in the numerator. And in the denominator, I'm going to get 1 plus 5 over x plus 6 over x squared. Based on what we just talked about, anytime you have a constant in the numerator and any power of x in the denominator, we know the end behavior on either side is always going to be 0. We just kind of proved that graphically. We can also look at some number sense, right? We kind of talked about this the other day, something very similar. If I do direct substitution with infinity, which you really can't, but in other words, as x gets larger and larger and larger, what happens to 1 over x? It goes to 0. So I'm going to write it like this. That's going to be 0. What happens if I plug in a really large number for x and I square it and it's 2 divided by a number that's getting larger and larger and larger? That goes to 0. Okay, so it's that idea that a constant over a really large number goes to 0. So I get 0 plus 0 in the numerator, and the denominator I get 1 because there's nothing to plug into. Then I have a constant over a really large number goes to 0, and then 6 over a really large number goes to 0. Right? So now if I do this limit, I'm really looking for the limit as x goes to infinity. Actually, you know what? I'm not really substituting, so I don't know how I want to write this. I'm going to say you can write it because we're doing direct substitution, sort of. So you can drop the limit here when you're plugging in infinity. So we get 0 over 1, which is 0. That confirms our answer of 0. So that's the other way you can do this if you don't want to think about the graph and the horizontal asymptote. You can divide everything by the highest power of x in the denominator. Let's look at this case. So if I do the same, the highest power in the denominator is again x squared. So I've got 2x squared over x squared plus 7x over x squared plus 6 over x squared over x squared plus 5x over x squared plus 6 over x squared. And now if I do my substitution of, first I got to simplify. As x approaches infinity, I get 2 plus 7 over x plus 6 over x squared. That was terrible. Let me try that again. X squared over x squared is 1 plus 5 over x plus 6 over x squared. Okay, so now we're going to do our direct substitution of infinity. So in the numerator, I get 2 plus 0 because, again, when you have a constant over a really large number, like infinity, or any power of x, right, it's going to 0 if I'm plugging in infinity or negative infinity. So same thing happens at 6 over x squared, and then on the bottom I get 1 plus 5 over infinity is going to 0, and 6 over infinity squared is also going to 0. So I end up getting 2 over 1, which is 2, which confirms what we said. So you can see when you do this method of division, I'm not going to go through and spell it out for you, but you can see how that leads to the rule of leading coefficients in degrees of x, right? When you divide by the biggest power of x, you see what happens. If the biggest power of x is on the bottom, then something happens on the top, and like I just said, I'm not going to spell it out, so I'm not going to, because then our video will be 50 minutes long. All right, so the last one, what happens when the degree up top is bigger? Remember, the rule is to still divide by the biggest power of x in the denominator. All right, so when I simplify this, I get the limit as x approaches infinity of x plus 3 plus 2 over x over 1 minus 1 over x. I can go plug in infinity, and I'm going to get a positive infinity plus 3 plus 2 over infinity goes to 0 over 1 minus 1 over infinity goes to 0. So it looks like I'm getting infinity plus 3 over 1. We know infinity plus 3 is infinity. Divided by 1 is still infinity. So that confirms our result of positive, or it doesn't confirm. We didn't know which one. So it's positive infinity. So another way to look at that is when you know there's a slant asymptote, when the degree is exactly 1 power higher, you can analyze these coefficients. When I divide them, I get a positive, so your slant asymptote has positive slope. So that'll tell you on the right side, if they're looking for x going to infinity, the graph's going up. And if they're looking for the left-hand behavior by saying x goes to negative infinity, the graph's going down, because these coefficients have a positive slope. Let's look at the next. Okay, so let's just look if anything changes or how we deal with when x approaches negative infinity, which is our left-hand behavior. Based on what we know about asymptotes, this has a horizontal asymptote at 2. So when it has a horizontal asymptote, that's because the degrees match, so we divide the leading coefficients, which is 2 divided by 1. And when there's a horizontal asymptote, the limit on the left as x approaches infinity or negative infinity have to approach that horizontal asymptote for these rational functions. So if there's a horizontal asymptote, that's your answer. It doesn't matter if it's right side or left side. Let's confirm, though, how we would do this. If you don't want to analyze asymptotes, you could always just follow that rule of dividing by the largest power of x in the denominator. We simplify. And then I can do a direct substitution of negative infinity. So I get 2 plus 7 over negative infinity still goes to 0. It's just it's approaching 0 from the bottom, so it's really small negative numbers, but it's going to 0. Plus 6 over a really large negative number, that goes to 0. It goes back to what we said on that kind of first or second page there. 1 plus 5 over negative infinity goes to 0. 6 over negative infinity squared goes to 0. So we end up getting 2 over 1, which is 2, confirms our analysis from the horizontal asymptote. So when it's a horizontal asymptote, infinity or negative infinity, nothing changes, because you're not really plugging infinity into anything in the end. You're just left with constants here. Let's see when the power on top is exactly 1 higher than the power on the bottom. So we know that's going to make a slant asymptote, and we know that that slant asymptote will have positive slope, because when I do the ratio of the leading coefficients, they're positive. So I know if I have a slant asymptote with a positive slope, I know that it's going up on the right-hand side and down on the left, so the function will follow that same behavior, because that's what a slant asymptote does. So they want to know as x approaches negative infinity, so they're asking about the left-hand side. It's going downward towards negative infinity. So that's our answer based on analysis of asymptotes. Let's do our little numerical analysis here by dividing everything, by the biggest power of x in the denominator. Okay, we'll simplify. We'll substitute in our negative infinity, so we got negative infinity plus 3 plus 0 over 1 minus 0. So this looks like negative infinity over 1 looks like negative infinity. That confirms the answer we got through the analysis of the slant asymptote. So let's just kind of try to summarize. I've been saying it over and over, but let's just make sure. So based on what we have seen and what we know graphically about the function above, would approaching negative infinity make a difference in the result of our limits? So as x approaches negative infinity, does not make a difference if the graph has a horizontal asymptote. But it would matter if the graph contains a slant asymptote. Oh, I forgot my M. So let's look at these without having to do the whole thing about dividing by the biggest power of x. Let's just look at asymptotes. So since the degrees match, the leading coefficients are negative 2 over 3. So yeah, that's our, I don't know why I just wrote it twice, but that is our answer. It doesn't matter if it's going to infinity or negative infinity. Once I see that we're talking about end behavior, whether it's infinity or negative infinity, there's a horizontal asymptote, so that's it. So they want us to explain our reasoning. So I'd say the degrees I'm just going to abbreviate here. The ratios of the leading coefficients is the value of the horizontal asymptote. Let's look at this guy. The degree is exactly 1 higher on the top because we have a degree 1 and a degree 2. So I know I have a slant asymptote. Now if I do the ratio, the 2 divided by the negative 1 makes a negative slant asymptote. So it's a slant asymptote with a negative slope. So now the function will follow that same behavior. So they're asking for the limit on the left-hand side because x approaches negative infinity. So the function's going to follow, I don't want the eraser, the function is going to follow that slant asymptote up to infinity. So there's our answer. So I'm going to say the degree, all that I just said, I'm going to write it out, of the numerator is exactly 1 greater than the degree of the denominator. So the graph has a slant asymptote say the slope of which is negative, since the ratio of the leading coefficients are negative. And we're just going to say from there, I'm not going to write out the rest of it. I mean, we know that since the slant asymptote has a negative slope, we can figure it out from there. So again, you kind of have choices. You can do this process, or you can analyze the asymptotic behavior. And keep in mind, I'm kind of not talking about what happens when the degree up top is less than the degree on the bottom. You always get 0. So we may come across some functions where it's a little bit trickier here, where we don't have just one horizontal asymptote. We may have 2 horizontal asymptotes. So here's a picture of a graph that has 2 horizontal asymptotes. And it's because when you square root x squared, the answer is not just simply x. It could be x or negative x, right? The square root of x squared could certainly be equal to negative 3, because I could write it as, here, let's look at this. Or it could have been written like this, right? So it could be negative 3 or it could be positive 3. So that's kind of what's driving this here, how we can get 2 horizontal asymptotes. So what's the one thing that's different? There are 2 different horizontal asymptotes. And remember, asymptotes are end behavior. So on one end of the graph, it's going to approach one horizontal asymptote. On the other end of the graph, it's going to approach the other one. That's why there are 2 of them. Remember that a graph can cross a horizontal asymptote. The horizontal asymptote is basically, doesn't even mean anything through the middle. Like if I wanted to, I could sort of just get rid of it through the middle. Right? It means nothing. It's more about end behavior. Through here, it doesn't matter. It's just showing you where the graph tends to go. So if I wanted to, I could sort of erase that. Just mentioning that or reminding you of that. All right, so now there's 2 different asymptotes. So use the graph to find these. So as x approaches negative infinity, we're approaching that horizontal asymptote of negative 2. As x approaches positive infinity, we're approaching the other horizontal asymptote of 2. So we can see it on the graph. Let's do some algebraic analysis so that when we don't have the graph, how do we figure out which one it's approaching, or even what those asymptotes are? We can do our division of our, there's two ways to think about this. I'll give you one way here in the video, and then I'm going to talk about another way in class if we need to, if we need a different way to think about it. So keep in mind that I was saying that the square root of x squared is really just x, but it could also be negative x, okay? Now, in either case, the degree of this is 1, right? When you square root a square, the degree is 1. So we're considering this to be degree 1. And this numerator, of course, is degree 1. So when I say divide everything by, this is how we're going to do this. Divide everything by the biggest power of x on the bottom. You're dividing by really an x. Now here on the bottom, we're inside our square root. So we're going to divide everything by x squared. That's the biggest degree of x on the bottom. But in the top, we're going to divide it by x. Why are we doing that? Why are we not dividing by x squared? Because really now it's not inside the square root anymore. We're really dividing it by the square root of x squared, which we know to be x. Now I keep telling you it could also be negative x. So we're going to decide up front when we do one of these, when we see a square root in here, right? We see the square root and we're doing x approaching infinity or negative infinity. we're going to decide which one it is and kind of write it up on top. So in this case, the square root of x squared is going to be equal to x. Why do we know that? Because we're plugging in really large positive values for x. So when we're plugging in positive values for x here, right, it has to come out to be x because x is bigger than 0. We know that because positive infinity. On this guy, we're going to write before we start, the square root of x squared is going to be equal to negative x. And that's going to help us with our analysis. For the other reason, by the way, we're plugging in really large values of, really large negative values of x. So if I plug in a negative number there, something less, where x is less than 0, it's negative. That means when the square root undoes the square, I end up with negative x. Okay? So when we divide the bottom, we can just divide by x squared because we're still in the square root. But up top, we're out of the square root, so we've got to divide by x. So that's why we're choosing x here. All right, let's simplify. We get 2 minus 2 over x over the square root of 1 plus 1 over x squared. So now we can substitute in our infinity. Oh, I'm plugging it in. I don't need to write that out. Sorry. I get 2 minus 0. 2 over x, or 2 over infinity goes to 0. Divided by the square root of 1 plus 0. So I end up getting 2 over the square root of 1, which is 2 over 1, which is 2. Confirms what we found up here. As x was going to infinity of this function, the limit was 2. I'm going to make this a little smaller. I'm kind of bleeding over to the other side. Okay, so over here, before we start this problem, we see that it's an end behavior one. We see that it's rational with a square root in the denominator, so we got to decide right away that the square root of x squared here is going to actually be equal to negative x in this case because we're plugging in really large negative values for x. Oh, I think this pen just died on me. Let me charge it real quick. Okay, so on this one, we're going to use our square root of x squared as negative x because of the negative infinity. So now we're going to use our analysis by dividing everything by the largest power of x in the denominator. So that's the square root of x squared. Again, since we're still working under the square root on the bottom, we just use x squared. Up top now, we've got to do the square root of x squared, which in this case is equal to negative x. So now we simplify. I get negative 2 plus 2 over x, and then 1 plus 1 over x squared. So now when I plug in a negative infinity, I get negative 2 plus 0 over the square root of 1 plus 0. So that's going to be equal to negative 2, which confirms what we thought about before with the slant asymptote and the whole thing. Oh no, sorry, this is the double. So yeah, this is how we do it. You're going to, the key is this guy, the start. Which one of these do you choose? And then we're dividing by the biggest power of x in the denominator. So these are confirmed by the graph up above. All right, let's try 2 more. So in this case, the square root of x squared is going to be equal to negative x, right? So I see a square root in the denominator. I see that we're using negative infinity, so this is how I come up with this guy. So if I divide everything by the biggest power of x in the denominator, remember up top it's negative x. By the way, these powers technically match. That's why there's horizontal asymptotes, because this degree is 1 and the square root of a square is technically still a 1 as well. Okay, so we then simplify. I'm going to get negative 3 plus 2 over x over the square root of 2 plus 1 over x squared. So when I plug in negative infinity, I get negative 3 plus 0 over the square root of 2 plus 0. So that's going to give me negative 3 over root 2. And then I don't know if you want to rationalize it or not. So we know also that this graph, since this is the limit, we know the graph has a horizontal asymptote without ever seeing this graph at negative 3 over root 2. And it has another one because we can, it's the square root of a square, so we know that there's going to produce a second one. All right, let's look at another example over here. So again, we're going to start by saying we have a square root in the denominator, and we're plugging in negative infinity, so our square root of x squared equals negative x. Now, this one's going to be interesting. It doesn't have a horizontal asymptote. How do I know this already? Because the degree of the numerator is 2, and the degree of the denominator is really a degree 1. So this will have some type of a slant asymptote maybe, but it doesn't have a horizontal asymptote. So that means our answer is not going to be a number. It's when there's not a horizontal asymptote, it's either going to be infinity or negative infinity. But we can just go ahead and work through the same analysis using our negative x when we're dividing by the biggest power of x. So in the denominator, I've got 3x squared over x squared plus 2 over x squared. Up top, I've got x squared divided by negative x plus 2x over negative x. So when we simplify that, that was a weird limit. I'm getting negative x minus 2 in the numerator. In the denominator, I'm getting the square root of 3 plus 2 over x squared. So when I plug in negative infinity, I'm getting negative infinity minus 2 over the square root of 3 plus 0. So I get a positive infinity minus 2 over square root of 3. So infinity minus 2 is still infinity, and then infinity divided by a positive number is still positive infinity. So that's how we work that one out. Not bad, a 42-minute video.